On the line. In listen-only mode.
Hello.
Yes, sir. Go ahead.
Hi, we can start now?
Yes, sir.
Hello. Hi, yeah, I am starting now. Yeah. Good afternoon, everybody, and welcome to this a long 25-session webinar course on glimpses of digital signal processing. Basically, the digital signal processing has much advanced in last few many decades rather, and compared to early 70s when it started its proliferation. As of today, there is substantial amount of spread of this subject all over the globe in all domains. However, some mystery which was there in early 70s still remains to some extent, and I perceived this while I was a student, and in so many years of teaching I find that there is now, instead of non-understanding, there is pseudo-understanding phobia or phenomenon which is being observed across all the batches at one place at one time at all the places. Therefore, I thought it fit to deal with this subject from a common learner's perspective. Learner-centric approach is now the theme in outcome-based education, but we hardly find that in conventional classical approach, the learner who is supposed to be at the center of the entire delivery is found to be wandering outside the periphery and in a confused state. Therefore, I will be deviating to a large extent from classical approach, but I will not be discussing something which is fundamentally diametrically opposite, but for a few beginning sessions one may find that the things which are being told are not being heard by us, or are something contrary to which is being taught in practice, and so on and so forth. However, the purpose being the appropriate understanding of a student, and now we find that even if we consider only India as an example, at least 1 lakh plus students undergo through this subject every semester, or at least in 1 year. And with this spread of education with different backgrounds of the students, it is very much difficult to teach this subject in a manner that the learner learns. And if the purpose is not satisfied, then whatever kind of delivery you have, it may be very much classical, it may be perfect in science, perfect scientifically, maybe grammatically, but it will not serve any purpose. Therefore, the focus of this entire course is from pedagogical perspective, wherein we deal with the approach with which this subject should be unfolded. The interest of a student gets developed based on the beginning sessions of a subject, and if we try to have beginning sessions in a classical manner, right from starting with symbols like X, Y, then capital X, then XN, XK, then tilde, and all these things, and bar, the student gets completely out of track. Therefore, this first session will try to introduce this subject, rather than this is a webinar course in which more than students, many teachers are also enrolled. Therefore, they should look it from the pedagogical perspective, and not that they are being addressed directly by me as if they don't know anything. We honor all the participants, but whenever the delivery is being done, the delivery is addressing a novice undergraduate student having hardly 10+2 background or first year of engineering. That's all. So we should start with this with no prerequisites, even though signals and systems is prerequisite in many of the universities. Somewhere we don't find it, somewhere they club 2 subjects in one. Therefore, we try to deliver it as an independent course. Then, what is most important of digital signal processing is it arises from the very phenomenon of signal processing. Means even below earlier than 70s, when digital signal processing was not there, signal processing was well spread in all the disciplines for different purposes. Therefore, signal processing is the main theme. Now, we try to deal with this, what we mean by a signal, what we mean by processing, what types of signals we deal with, what is their real life significance, what is their modeling, what is their representation, and I would also try to specifically focus the two-dimensional nature of signals, because that the very concept of using complex numbers as regards to algebra, as regards to calculus, if these two are concerned, the complex number theory plays a very crucial role, and as I have found that the students are unable to understand it, are unable to understand its purpose, and get confused with imaginary term, electronics engineering being most of the proportion imaginary, and in that the very concept of an imaginary number, an imaginary term leads to square of imagination and in confusion of a student. Therefore, now we have a slow, definite, but well-directed approach in dealing with this entire subject. So we deal with now a signal and its processing. Its processing corresponds to some kind of signal input is applied to such a system. The components of that system are such that the signal applied is able to have some kind of effect to the components in the system, and then from somewhere of the system we are able to get another signal. The first signal is called as input signal. It undergoes into a system, produces some effects on the system, hampers or makes an impact on the system components, and we are able to, or makes the system to deliver some other signal, which is output signal. So input signal, system, and output signal. It is the phenomenon. Then which signals happens to be a more significant approach, because we find that in practice we deal most of the times with voltage and current and some electric circuits like consisting of R and C, to which we will come after some time. But things being imaginary, the perception of an individual which is being created out of the systems which are electrical systems, even though it is convenient to deal with, even though electrical energy is in such a good form so that it can be converted from any type of energy or into any type of energy, and most of the times deal with as a central theme, we find that electrical signal is normally not a real life signal which we encounter with. Therefore, taking RC circuit, applying some voltage to it, and finding output from that RC circuit means what we find is most of the times we deal with, many of you might have observed that you deal with the circuit like this, you draw a capacitor, you draw a like this, you continue on this side, you continue on this side. So this is an input and this is an output. R we can take 1 ohm, C we can take also 1 farad. Here we apply as V in, and it is being varied, V in T, and here we try to obtain VOT. But the major problem is that how many times you may convince, but the voltage signal is no doubt a signal, no doubt a proper signal, but to have an impression that voltage signal is, I make a very meaningful statement that voltage signal is not that way a real life signal. Voltage signal is not a real life signal. This being the fact, we try to deal with it like this. So just I am completing this correction, which is not so important. This is input, this is input, and this is output. So conventionally, the first component in analog systems in the signal system part is taken as this, but as I had already stated that this is not a real life example, and therefore I will specifically turn to a real life example, even though it is very simple. This is such example which everybody can understand, and the real life example which I am going to deal with is of fluid dynamics. It is a simple water level model to which we will come. I will explain all the simple assumptions. It is very simple, but the message it conveys to a student is most significant. The purpose of a session should be, from simple things, a very significant message should be delivered. From significant things, if the message is not delivered, the things are of no use. Therefore, we will proceed step by step and lead to a differential equation. Differential equation is the key theme in signals and systems, both analog first and then its conversion to digital. But the differential equation and its solution is no doubt good classical thing and is having centuries of existence. It is, differential equation is not considered as an easy cake by a student. Therefore, sometimes we find that the generations today are more lucky than generations earlier, because they have with them a differential equation and they have with them a good tool to solve that differential equation, so that the difference equation, because it is very simple to understand. Now this water level model, which I had very specifically developed, few themes have been original here, and we shall proceed with them. So introduction to systems now, it's a major theme. Ohm's law is being taught even now in high school days, and when we teach Ohm's law in high school days, the problem is that the electric voltage is applied to a resistor, and depending upon voltage and resistance, I is equal to V upon R. I equal to V upon R is told, but the problem for, I claim again, that this leads to a pseudo understanding, because what is voltage is something which is not perceivable for a student. Therefore, a very nice analogy has been developed for the water level model. One, you might be looking one figure here. Only thing is that I have just forgotten that the highlighted spot, there is a water tap which is being continuously feeding the water, so that the water level in the first tank is always maintained as L1, and for the second tank we are having the exit, so water level there is always maintained as L2. So one correction is that at the highlighted place, which is now the box, there is a water tap and water is always flowing there, because in most of this example you will not find anywhere. This is just an example to explain Ohm's law. What I want to create now, I want to create a first order water level model system in few minutes from now, but for that the theme is very important. Now what we find, it is very clear that we have water level and electrical engineering analogy, wherein you will find now that flow, which is F, it is in quantity per time, maybe cubic meters per second in what we can say IS units. Flow is equal to, it is very clear, that there is a valve. Valve has the pipe which I'm showing the pipe. The highlighter component here includes one pipe which is flowing up to the wall, and after the wall again there is a pipe. This pipe is presumed to be carrying zero resistance, whereas the wall is having an adaptable opening, so that small opening would be large resistance or more opposition, large opening would be having less opposition. So it is very clear that there is a simple 1:1 correspondence. Current on electrical side, just there is, I'm extremely sorry, there is one for the first, it is the sequence is reversed, that current is electrical side, flow is water side, potential is electrical side, level is water side, resistance is electrical side, opposition is water side. So just like I is equal to V1 minus V2 upon R, similarly flow is equal to level difference, just like current is equal to potential difference upon resistance, similarly flow is equal to level difference upon resistance, L1 minus L2 upon O. Flow is L1 minus L2 upon O. And the last point which is remained, then what is equal to electric charge? And the answer is the actual water quantity itself is equal to electric charge, because flow is rate of flow of charge with respect to time. Similarly, water flow of water itself with respect to time. Now, this is most significant model for a valve. A valve is a resistor, and the flow from a valve is proportional to the level difference across two sides of the valve. So valve is now modeling my resistor, and now the most significant thing starts is the RC circuit model. Here again, I am extremely sorry, is that just the water tap is also supposed to be here at the first tank. At the first, no, it is not a tank actually. L in is maintained by the outlet, and in that continuous water is flowing. In the highlighted portion, there is a water tap which is always maintaining L in, and also the platform is a movable platform. It's most important, and this pipe which is having is of flexible length, so that I can move the platform up or down, which will change L in, and the next is the tank having cross section. It's a cylindrical tank having cross sectional area A, which models a capacitor. This being cylindrical, if it is non-cylindrical, it will lead to further complexity. To that I am not coming right now, but I will come at a later stage. Now what will happen? The output level, or the level of the tank, level of the water in the tank, is called as L out. This is the base level. Base level is very clearly shown. The base level, just I am plotting the line. That is, presently the wall is at base level. That the same horizontal level of the wall is base level. The movable platform can change the level so that L in can change as a function of time. Initially there is a stopper. Initially in the highlighted portion there is a stopper shown. That stopper is just like a disconnect, just like a switch in my RC circuit. When I open the stopper, the things start, and once it is open, the things will change. The valve is having a portion O, just like resistance R, and for capacity it depends upon something on area. So now I again say that we should now try to derive an equation of L out and L in. We should try to derive an equation which governs the relationship between L out and L in, and it is actually L out and L in are functions of time. So even right now in the first formula, what you are observing is flow F is equal to L in with respect to the wall. Wall is a resistor, So first potential on the other, level before the wall, level after the wall. Level before the wall is L in, level after the wall is L out. So L in minus L out upon opposition O. I hope that the idea is very clear, that for a valve, the flow allowed by a valve is level difference upon opposition. Therefore, we can find that the flow here is L in minus L out upon O. Just I move ahead, and now I say that since these are functions of time, I make them with bracketed with t. So ft is equal to L in minus L out, L in t minus L out t upon O. It is presumed, and it is quite obvious, that wall is having constant resistance. It doesn't change with time. It is a reasonable presumption. Now it's a very interesting circuit theme will develop. What will happen? Suppose if initially there is no water in the tank, the stopper is closed. If we have put the movable platform such that the L in is 1, and if I open the stopper, what will happen? That any novice can also say that the moment at which the stopper is opened, the water will start flowing. The water will start flowing is the cause. Then water starting flowing is the cause. But what is the effect of that? The water will start flowing from the left source, will now move to the right tank. Why it will move from left to right? Because initially the level on the left hand side of the wall, which is L in, which is say 1 meter, and one more important thing is that L in is maintained constant, because I had forgotten that is here there is a tap which is continuously supplying the water. So the water in the left source is always maintained at the position shown, and as it is always maintained at the position shown, we find that it will maintain. It is the cause for the flow, but when it is causing the flow will be from left to right, and that flow will now move the water into the tank, and the tank does not have any outlet as of now. As the tank is not having an outlet, the flow will result into storage of the water. Flow will now result into storage of the water. That storage of the water, what is the effect now? The effect is the level in the tank, that is L out, will start increasing. And here is the crux of the entire theme. What was the cause for the flow? Cause for the flow was the level on the left hand side of the wall was 1, level at the right hand side of the wall was 0. So level on the left hand side of the wall was larger than level on the right hand side. Flow started, but so the level difference started the flow. That is, level difference is the cause and flow is the effect. But the effect is now increasing the level in the tank, that is the right hand side level, and it will now have an impact on the cause. The cause is leading the effect, and now the effect is changing the cause. How? In what manner? As the level in the tank rises, the level difference will reduce. Level difference will reduce, and as level difference reduces, as per my earlier formula, which everybody has agreed, that level difference minus upon O being fixed, the flow will reduce. So the flow which was there when I opened the stopper will not be maintained, and that flow will reduce. But the flow direction will remain same. But as the flow is reduced, the flow reduction will also reduce the quantity which is being put into the tank at a certain rate. That will reduce. So that will also reduce the level, that will also reduce the rate of rising of the level of the tank. The rate will be reduced, but the level will increase. Level will always increase. Level of the tank increasing will again further reduce the level difference, which will further reduce the flow. So what is the common sense non-mathematical conclusion is that the flow which started at the opening of the stopper will always reduce, will continuously reduce and the level will continuously increase in the right hand side tank, but the rate at which level increases will always reduce. So the level of the tank will increase in an always reducing rate. Now we will start to put it mathematically. Now, how do we relate the water quantity in the tank and the flow and the area? Water in the tank is area into level, that is L out. Why? Because it is a cylindrical tank whose cross-sectional area remains same throughout the height. For non-cylindrical, or for those tanks whose cross-sectional area is a function of height, we will deal with them separately. So right now, water in the tank is area into level. So at a particular time there was some level, means there was some water. After some time, if the water is added, or for given water quantity there was some level. When we add the water, the level will rise. Now, I am making few statements which may be prima facie that in the system, when I open the tap, open the stopper, initially it was at 1, in the left hand side the source was 1, the right hand side tank was having level 0, I open the stopper, the water will start flowing, but the flow is always reduced, so the water flow will never be constant. Why it will not be constant? Because the flow starts, level reduces, flow reduces, but level again increases. How much water is added into the tank? In that case, answer would be flow into time, but unfortunately, flow not being constant, you cannot apply flow into time. Therefore, it has to be integration, but again, that integration means something which is somewhat clumsy, which creates some phobia, which creates some inhibition for the student. Therefore, I will not jump to that right now. What I will presume that in a very the flow is changing, but the flow is not changing abruptly. Therefore, if I presume that delta T is infinitesimally small area, for water systems, what I say, some millisecond is a negligibly small area. Delta T is say 1 millisecond, for example, not necessarily. It is always a small, infinitesimally small time interval. So in that, we can presume that Ft is piecewise constant. It is not constant. I am not contradicting. I am agreeing that it is varying, but the variation for that particular small interval is in ignorable range. Therefore, what I can say, that if at time t the level of the tank L in the tank was L out T, then in the delta T time interval, the water added is Ft into delta T. So if water is increased by the quantity Ft to delta T, it is very clear that for a cylindrical or for a such kind of tank whose cross-sectional area is constant, the quantity is cross-sectional area into level. So level is cross-sectional area, level is quantity upon cross-sectional area. Therefore, we can very easily say that if Ft delta T, you can highlight, you can see the highlighted text, if Ft delta T is the water quantity added, then the water level will increase by an amount, again you can see highlighted portion, Ft delta T upon A. And so we can have a very simple equation. If you concentrate on this equation, if L at time L out was the level, L out T, then at time T plus delta T, L out T plus delta T would be L out T, means water level is going to increase. So at time T plus delta T, the water level would be whatever was the level at time T plus the level increase during time delta t, and we have seen that the quantity increase is ft delta t, therefore level increase is ft delta t upon A. And now by simple mathematics, the equation can be rearranged such that ft is equal to A into L out. You can look at this equation. ft is equal to A into L out at t plus delta t minus L out t upon delta t. Now, this is very significant equation. What delta t we are supposed to presume? Delta t is supposed to be infinitesimally small as possible, and it should tend to 0. And therefore, by the first principle, if we ignore A from this equation, then the remaining part, that is fx at f of x plus delta x minus fx upon delta x, that is equal to derivative. So we find that it is L out, which is a function of time. So L out t plus delta t. Instead of f, it is L out. Instead of t, it is x. Instead of delta t, it is delta x. So we can find that it is the derivative of L out versus it's a time derivative of L out. So d L out, the bracket t is, you can, here the bracket t either can be specifically put or it can be presumed. So ft, this equation is very important. Ft is equal to A into dl out t upon dt, or dl out upon dt, or f is equal to A dl by dt, that is the flow is derivative of the level, output level. And now this is equation number 2. I would like again to draw your attention to equation number 1. Equation number, this is in the equation number 1, this is O, not 0, otherwise we will say it's divided by 0. So ft is the wall wants ft to be in a particular manner. It should be L in t minus L out t upon O. The wall wants the flow in some particular manner. The tank wants flow in some other manner, and this is a series circuit. It's a connection, there is no outlet in between the wall and the tank. Therefore, what is obvious is that for a series circuit, as the current is constant, likewise the equation number 1 is dictated by the wall. Equation number 1 is conditioned by the wall. It is the wall characteristic which imposes equation number 1. Equation number 2 is imposed by the tank characteristic, and since it is a series circuit, the equation number 1, the flow imposed by the wall must be the flow imposed by the tank. They must be one and the same, and therefore dl out t upon dt is equal to L in t minus L out t upon O into A. This is now a classic linear differential equation with me. But again, what problem occurs is that O into A is a term which is some constant. It is like an RC product. On electrical equivalent side, O is corresponding to R. Large O means large R, and large capacitor means a tank with large area. So A represents C and O represents R. But we try to further simplify. And further simplification is by the phenomenon, that is, if we choose, we have option to choose, and at the beginning, whenever we have option to choose, we should choose a simple using O and A such that the product O is equal to 1, and if it is so, the equation is further reduced. It is a very nice looking linear differential equation, that is dl out t upon dt plus L out t is equal to L in t, and the bracketed t is presumed, and so that I am not writing it specifically, and rearranging in a classical form d L out T upon dt plus L out minus L in is equal to 0. This is the differential equation. And now this differential equation is universal for this entire tank model. Mean to say that at the beginning I said that the tank should be empty, the stopper should be closed, and I open the top stopper at t equal to 0, and after that system begins. But once we can presume that the stopper has been opened at some time and the system is in some state right now, then what we can further have? We can further have a liberty. This is a movable platform. This platform you can move as per your desire. You can put it on some mechanical arrangement and you can move it up and down. You can move it in a linear manner. It is a triangular wave. You can move it abruptly. It is a square wave. You can move it in simple harmonic motion. It is sinusoidal waveform, and so on and so forth. Or you can hold it in your hand and you can move it randomly. And for all the kinds now, so the stopper you need to forget. The tank was initially empty, that you need to forget. The differential equation which we have derived, because neither the equation number 1 nor the equation number 2, neither the equation number 1 nor the equation number 2 have a precondition of the stopper, initial state of the tank, or anything like that. Therefore, the final differential equation which I have written, that d L out upon dt plus L out minus L in is a universal differential equation for my system. And I hope that while constructing this differential equation, we did not require any preliminary knowledge. The fluid dynamics is very easy to understand. The only presumption is that the flow is linearly proportional to level difference, which may not be exactly correct, but the presumption is a very reasonable presumption, and is linearly proportional to some opposition. That it may not be, the opposition O may not be linearly proportional to exact opening, but we can define some opposition, we can define some level difference, and we can very conveniently presume that level upon opposition is flow. And based on that single presumption, we have got this differential equation. The solution of this linear differential equation in itself is also not so easy. What happens is that the classical solutions are learned by a student in a different context without matching them to actual application, and then the things are again leading to some kind of confusion or chaos. So to this I will come in next session, but right now what was the purpose of today's session? Today's session is not over. We are switching to part 2 of today's session. Today the purpose of today's session was to give the concept of signals systems using real life examples, and we defined it in continuous time, and in continuous time when we define, we led to a differential equation. Or what is called as sampling. Means what? Again, that sampling theorem, that why the twice sampling is sufficient and all that. If it is taught at the beginning, then it may not be able to give a good impact. What we can think is, instead of continuously watching the levels, which I even cannot watch, what we can think of is, nowadays every student carries the mobile, and now what is the good example of sampling that I am saying now? We have actual system, the water flow is there is a left hand source, there is a middle valve. I hope that the picture is not before you, but the picture is on your intellectual plane. There is right hand tank and the system is flowing, and I am having a movable platform and I am moving left hand source. Then there are two options. You yourself watch the entire thing. You yourself watch what is LNT at every instant, what is LOT at every instant, and what is flow at every instant. The flow you cannot perceive to that extent, but ultimately we don't want flow also, because the final equation what I'm having, I'm interested in for what kind of O and A, means for what kind of valve opening and for what kind of tank, what would be impact of L in and LO. I want to study the interrelationship between output level and input level. In what manner the output level changes for what kind of input level for a given system. Given system means given opening and given cross-sectional area. So flow becomes redundant. Not redundant means right now I don't need that. So what you can see, if you are continuously watching on your own, then you are having with you directly LNT and LOT, everything you have at every instant continuously. Or you can record it using mobile. But what happens is that watching continuously, nowadays we are smart enough that we even don't want watch various programs continuously. A new theme is being come that you can watch two TV sets. You can have two TV sets and you can watch two programs simultaneously by only watching one at a time, and after some time switching to the other and having suitable switching frequency. Like that, I hope that those who are teachers may now understand that I am coming to sampling. Instead of continuously recording on mobile in the form of video, what I can do, instead of continuously recording, what I can do is, I will be taking the actual water experiment is being conducted and I am having good mobile, I will take snapshots, each snapshot at a second. So in 1 second there will be 1,000 snapshots, in 1 minute 60,000, so and so forth. And at each snapshot, I will be having a concept that there would be level in, there would be level out. So I would like to give you at any given snapshot, you just look at the highlighter, at any given snapshot. So n is now an integer, n is 0. Actually when I say first, we start from 0. It is a convention and useful in many for many purposes. Right now we don't go into the details. So first snapshot is taken. Whatever level input is seen in the first snapshot is L in bracket 0. What is level seen of the output tank in first snapshot is L out 0. When in the next snapshot, so n is equal to 0 for the beginning snapshot. Then for the next snapshot, n is equal to 1. For the next snapshot, n is equal to 2. So n is an integer index moving from 0, 1, 2, 3 and endlessly. So if you record it for 1 minute, then you will be having 60,000 snapshots. Now, instead of dealing something in continuous manner, we try to deal it in discrete manner. How? So we can say that at given sampling instant, n is snapshot number, is the nth snapshot. So what the equation number 3 which is before you is the status of the system at the when the nth snapshot was taken. When the nth snapshot was taken, the status of the system was the input level was something, output level was some other thing, which we define as L in bracket n, output level is L out bracket n, opposition is O. So at that instant there has to be some flow. Flow n is not captured in snapshot. Flow n is not captured in snapshot, but I am sure that you would be able to perceive it very easily. If so, the flow which was there when the nth snapshot was taken is Fn is equal to L in n minus L out n upon O. Now, our sampling interval. What is sampling interval? It is the time between two snapshots are taken, for example 1 millisecond here. So capital T is sufficiently small. What is sufficiently? Then we need not go to sampling theorem that twice the highest frequency component. That is something which is beyond understanding of a common individual. When I say sufficient, sampling should be sufficiently fast, or sampling interval should be sufficiently small. Means what? Compared to the changes in the system. Water is somewhat sluggish system, we can say. So for water system, I can very easily say that 1 millisecond is sufficiently small interval, so I can very peacefully choose capital T as 1 millisecond. If it is so, then in 1 millisecond, the water which would be added is the flow into 1 millisecond. Then again you may question. What you may question? Whether in that entire millisecond, the flow in is constant. It is not. But I can safely say that it is not changing by such a level of which I should take cognizance. Therefore, I can safely say that for 1 millisecond, what was the flow at the beginning of that sampling interval, what was the flow at the time of beginning of the nth snapshot, is there or is changed by such amount which I should not consider that the water which is added in between two snapshots, nth snapshot and n plus first snapshot, is Fn into capital time T, and obviously when the water added is Fn into T, the water level which will increase will be by water added upon area. So Fn into T upon A, and then I can proceed further. So what will happen? L out. What now? You concentrate on this equation which is highlighted. Let us wait for some time. It is yet to come. This being an audio webinar, you may not be able to see it in. And now you are observing that the highlighted equation. You can observe that L out n was the output level in the nth snapshot. L out n plus 1 would be the output level in n plus first snapshot. And by what amount they will differ? The L out will increase. L out will increase from nth snapshot to n plus first snapshot by a value water quantity added upon area. That is L out n plus 1 is equal to L out n plus Fn into T upon A. That means now Fn is equal, now you look at this fourth equation number 4, Fn is equal to A into, there is one mistake. What is that mistake? Is that there should be bracket for after the dot, A dot bracket L out n plus 1 minus L out n upon T. I am sorry for that. Now if you look equation 4 and equation 3, if you look equation 4 and equation 3 is again coming, it is just taking some time, you will find that the flow must be constant. Therefore Fn will go out of picture and I will get an equation in terms of level only. So from 3 and 4 now you come to the highlighted equation, that is from 3 and 4. Now you must be able to see the equation, that is L out n plus 1 minus L out is equal to T upon OA into bracket L in at n minus L out at n. That's all. So you can just look at, I will just make it small. So this Fn you are substituting, this Fn you are substituting in the previous equation, and by that you get the equation L out. So now what we are having here, most simple thing is that everything is in my understanding domain, because L out is a snapshot, L in is also a snapshot. In the mobile picture I can see the levels distinctly. I can write a very nice difference equation. So now I see here, this is a classical difference equation. It is actually equation of an IR system. To that I will come slowly. So here again, if T is something which I am sampling, O and A are again some constants. Now if I use the entire term T upon OA, if that is some constant K, in that case my equation is further reduced like this. It is just numerical rearrangement. L out n plus 1 I want is equal to L in n minus L out n into K plus L out n, wherein it is again very easy. Just what I mean to say is L out n plus 1, that is the output at next snapshot, has to be, it is a common sense equation. What sometimes or in general it is always my approach to get rid from a cascading effect. For a student who joins late, for a student who doesn't understand something, irrespective of that, even if you look the highlighted equation, it is very clear. A common man can say that L out n plus 1 is, you look at the second term of right hand equation, L out n plus something, and what that plus something? That plus something is proportional to flow, and the flow is proportional to L in minus L out. So irrespective of any of the previous discussion, even that this equation, highlighted equation, can be easily understood, that the level at the next snapshot of the output is level at the previous snapshot plus level added by some amount. And level is added by what amount? Level is added by something proportional to flow. And flow is what? Flow is something proportional to level difference. And what is level difference? Level difference is again the level of input at nth snapshot minus level of output at nth snapshot. So it's a classic equation. And again, by rearranging the terms, I can have L out n plus 1, I just multiply the terms, is equal to K into L in n plus 1 minus K into L out n. And again, in general, L out n, what I can do is that n plus 1 I have taken, but normally we don't take. So you can substitute n plus 1 by m. So n will be m minus 1, and again in that substitute m by n, or in general instead of n plus 1 you can, if you choose n, then n will become n minus 1, because it's in a classical terms which usually nobody understands, it is time invariant system. So L out n is A into L in n minus 1 plus B into L out n minus 1, is now in classical terms Yn is equal to A into Xn minus 1 plus B into Yn minus 1. Just what I made one change is that the bracket is made square bracket, which is generally done in discrete time systems. So Yn is equal to, that is the current output is a linear combination of current and past outputs, past inputs. Here there is no current input, but there is past input. If now I want to draw your attention at this equation, this complete equation, that is this equation, highlighted equation, you can see current output is a linear combination of a past input, this is a past input, and a past output. Current output is linear combination. A is constant, B is constant. So it's a linear combination of current of one previous input and one past input. This is a standard IIR DSP equation, and for given opening of the tank, now the question would be, what you achieved, for what purpose this entire discussion was there, and that we can see, that is what you did is, for given a position O, that is what was for a given valve, then I had given A, that is the given tank. For that, what I resulted, I was able to now Yn, or Yn I can use, that is the output level, instead of L out and L in, which is no doubt good, but sometimes we are so much prejudiced to even symbols that we feel this is better. Plus B into Y n minus 1. To be precise, this is x minus 1. This equation which I have derived is derived for carrying out simple understanding, but whether it is x n minus 1 or actually when I am computing, I had not gone to those details, but the flow which was constant, is not actually correct. The flow Fn was based on the flow between nth snapshot and nth plus first snapshot is something which depends on the levels at n and levels at n plus 1, because it is average. And when I am considering average, there is one way by which I can also presume, I can also introduce some concept of the input at n plus first. Therefore, this particular, whether it should be x of n minus 1 or I can choose by some other constant a1 into xn, means it is actually this discussion I am doing it, but I am not classically explaining, but I can also write that yn is equal to, let us say, a1 into xn plus again b, or for that I can change somewhat b into y n minus 1, which looks like more appropriate IR system. In fact, this is also an IR system, but one feels that the output yn is not having any dependence on xn, which is not so classically get. This my entire discussion is not of beginning level, so beginners may not understand, but this I can also write in approximate terms. Yn is equal to a1 xn plus b1 yn minus 1. Current output is a linear combination of current input, past input is not there, and past output. Or if I want that, if somebody is more interested, then I can also say, exactly is correct or not is not out of question. Anyway, we are writing out very approximate equation. Yn I can also say is a1 xn plus some a2, or to be more precise, a0 xn and then a1 xn minus 1 plus b1 yn minus 1 is also can model it very clearly. That is, now what happens? It is the xn, that is current input, one past input and one past output. So with this we are able to develop an equation, whether you choose this or whether you would like to choose this. You can choose this as well, you can choose this as well. So what we mean by these equations? We mean by these equations is, for now a given system, for given O and A, even if you forget this, because this is also all right, no problem. For given O and A, I can find out A and B, so that what I am able now, X is the input change and Y is the output change. So if I know the opening of the valve, the area of the tank, I can find A and B. For that, how to exactly find, we may take some exercise. I can write an equation now wherein I am able to, X can change in any manner. You can move the, now I will again switch to my previous one. What you can do is, I'm just concluding, we can, this movable platform, what I'm having, you can move as per your desire, either by hand or by some mechanical arrangement, so that you can completely capture the input changes. You can capture output changes. You can derive small a and small b for given opening O and A. And with this, it is possible that you are able to, what is our aim? For given system, what is the relationship to an input? And at the end, we can find that we have been successful in finding out the, ultimately, the relationship between, for given system, I can find out the output based on the input. Now, just I will conclude with some exercise for you, is that what will happen, other thing remains same, that is up to valve, everything is same. On the left hand side of the valve, everything is same. And on the right hand side of the valve, if I take the tank to be a conical tank, if the tank is conical tank, developing the differential equation or the difference equation for this given system itself is a challenge. That is because now the quantity is no longer level into area. The quantity is depending upon, or that is the quantity added into this tank will increase the level, not by fixed amount for the same quantity, but it will depend upon what was the state where the tank was filled and what was the, based on the previous level at which we started filling, the constant quantity will increase the level by different amounts. So hello, yeah, so I was too preliminary, but from next time we will be going to advanced things. The course web page which I am having would be operational from Monday evening. The course web page which is notified to you will become operational from Monday evening, and the homework assigned is, hello,
We can hear you, sir.
Yeah, I'm concluding. Hello. The course, the homework assigned, which is the tank example, this example, a conical tank. The solution for this I will be putting on the web page by Wednesday. From Monday, you can access the web page. I will be putting some material. Some time is given for you to have complete homework. On Wednesday, I will be putting the solution on the web page. And next Friday, when we meet, we'll proceed further. I can take up the questions now also, but since it is going to be a long course, and somehow even though I had planned the lecture this time, but still I took 6 minutes more. So I can either take up the questions now, or you can put the questions which will be mailed to me. And since this being a course, instead of answering the questions live, the questions, if any, if are text by you, would be available to me through mail. And in the recap, in the next session on next Friday, I can answer a few significant questions that time. I hope today we have somewhat eaten our time of 10 minutes, so it is better to conclude now. And the questions, I'm ready to take up the questions, but I can deal the questions later also. So